All right. Sort of an issue, I guess you could say. I have live chats all visible. So anyone that wants to chat, please do. I may not see the chat very easily, actually, and that's because of the camera. This is actually my phone. So the camera obviously isn't really going to be pointing towards me at all times, or it's going to be pointing at the camera at the amplifier. So the phone's going to be pointing towards wall, obviously. So now that that's out of the way, quick disclaimer: I didn't really do this at the beginning of the first video last night, and that is if you don't really know what you're doing with high voltages or electricity in general, please do not try any of the work that I'm going to do. I'm not really going to do any work necessarily, but I am, however, going to show you how these things work. Last night, it was more of just a passive discussion. There was no electricity connected to it. There was no wiring, nothing. And now I actually have wiring, power wires hooked up to it. Going to look at the waveforms of the half bridges that I told you about for the transformers. We're going to actually discuss what the transformers actually look like on the bottom without having to remove one. Now, this again is the Sound Qubed 4.5 kilowatt amplifier. It is a mono block and it is 1 ohm stable. Now, just to clarify the misconception of these amplifiers that I get all the time, why, if it's a mono block, is it a 2-channel? As you can clearly see, it appears as though it is a 2-channel amplifier. It is actually 4 electrodes. Well, in all actuality, it is 4 electrodes, but it's not 4 channels or 2 channels. This is the positive and this is the negative, but these two are connected together and then these two are connected together. And as you can tell, it is the exterior, the external connections that are actually connected to these wires. So if you are going to run the amplifier using only one set of the connections, I really recommend using the outer wire, the outer terminals, because that is where the power input or the power output wiring is directly connected to. It's called direct leads. Now, both of these are positive, both of these are negative. So that's just a quick clarification. Another quick clarification would be, I get this question asked to me, I don't know how many times when people come into this shop for me to check out their amplifiers. How do you turn on an amplifier without a head unit? Well, it's actually quite simple. And once you figure it out, you'll probably be mad if you've ever tried this. And if you ever try it, you can't really screw up, even if you do it wrong. Because if the amplifier is built correctly, it'll have a protection diode, and nothing will happen if you connect the connections incorrectly. Not the power. Do not, no, that's not what I'm talking about. The remote lead is, as it is discussed, or sounds like, it is a remote connection. So what that means is, instead of turning on and off the 12-volt input, or the 14.7 or whatever the input is when your car is running, that would require a big-ass switch that is very high current, and power losses would still occur. So instead, you send signal to the center terminal, which is the remote lead, which, just like with this little inverter here, you will have this connection. And these, do those look a little bit familiar? That's because they should, because they're in there. Now, this is called an inverter, which also uses a quadrature oscillator. This is actually very, very similar to a Class D amplifier. In fact, if I play my cards right, I could possibly convert an inverter into a Class D amp. Now, again, don't ever try and do that unless you know what you're doing, unless you have the proper equipment, because it does output 120 volts, and this main capacitor can be charged up to 200 volts, normally 150 to 170 volts. Aside from that, you send a small DC signal from the head unit, from the remote lead, into, if it was this, to one of these pins. And this, it doesn't use a remote lead, it just is a switch that's in between the positive power wire and the power input of the IC that controls it all. Now, in your amplifiers, you will see transistors, which act as buffers and that can deliver enough current And this transistor right here, more than likely, I haven't reverse engineered this amplifier yet, but that transistor right there, more than likely, is your remote transistor. And it's pretty simple to find out. And for some reason, this thing is not wanting to work very well. What happens is your head unit will send out a 12-volt signal, and it has a transistor inside it as well. And that's why it's only on when the head unit is on. And it sends power and turns this transistor on, closes the base, or closes, it sounds backwards when you think of closing the base or closing the gate, because in reality, in physical terms, that would mean nothing could flow through the gate. But since this is electrical, when something is open, the contact isn't made, so electricity cannot flow. Now you hear people on YouTube refer to it opens a transistor and allows power through. That their terminology, what they're trying to portray is 100% correct, but how they're saying it is a little bit off. And that's only because when the transistor is open, then it's as if it's not there and it does not allow the voltage to pass. But when you close it, it closes the switch and allows voltage to go through. And that's what happens here. It simply allows power to come from the direct 12-volt input. And I'm just going to say power input terminal directly to your transistor and to here. So to turn on a head unit to turn on an amplifier without a head unit, you just simply jump the 12 volts or the power input terminal straight to the remote. And that's actually how I do it here. You just take a small wire, and it can be very small, hence how the power wire, the remote leads are small. But I don't like to use really small wiring because you get noise, it just can cause interferences, all that kind of stuff. But you simulate the head unit sending out that DC signal. So what happens is you jump it and it turns that little transistor on. So for some reason, my camera is really weird today. Okay, so now that that is kind of explained, you just take a little wire from your remote lead and jump it directly to your power input terminal. And the reason I'm saying power input terminal is because some amplifiers can run all the way up at 18 volts. So obviously it's not 12 or even 14. That's 6 volts higher, which is quite a bit higher. And this amplifier is compatible with that. It is able to be run at 18 volts. However, on the Qubed website, when you look at the technical aspects of this amp, that will void your warranty. You can run it from 12 volts to 14.1, even to 15, I think even to 16. But if you tell them that you ran it at 18 volts, it will void your warranty, because what that does is it causes your output, it causes your power supply to be at a very high voltage input. So the duty cycle is going to be a lot stronger. It will also possibly affect the frequency of your transformer power supplies, of your half bridge, if you remember. And that will also affect the direct voltage output, because these are a switch mode power supply, but they are not necessarily regulated. I don't know how to say that. They are regulated, but the voltage output is dependent on the voltage input. So if you run it at 18 volts, the voltage on the output is going to be really high. Now, obviously, yes, you're going to get a lot higher wattage output, but at the possible consequences of burning up something, possibly your capacitors or your rectifiers, or more than likely your output stage. Now, the amplifier can run at 18 volts safely, but if it burns out, they just simply will not warranty it for you. Now, I do not know if he ever ran this thing at 18 volts. I couldn't ever really get any true information out of him, because apparently he didn't have it wired up properly either. He didn't even know if the fuses were blown. It's like, how do you not know that? If you're going to send an amplifier into me to get it rebuilt, or, well, to any shop to get it rebuilt, try and have your facts. Try and have as much information so you can give us as much information as possible without it being without it, it's just a lot harder. Because he said at first the fuses were blown, and then he said, well, no, the two fuses up front under the hood were not blown, but the one in the back was discolored. And I said, one. Well, the problem is I don't ever recommend wiring it like this, and this is why. He had, as you can tell, this actually does have two power inputs. So two 1-aught gauge terminals for the positive and two 1-aught gauge for the negatives. Now, if you're going to be powering, like running this amplifier with a load, I do not ever recommend running an amplifier that has dual terminal inputs only running with one. Don't ever do that. That will cause imbalancement in your loads. As you can tell, this goes directly here, and this does go directly here. Now, they are connected onto the PCB directly, so if you read with a multimeter, it is a short between the positive and between the negative terminals accordingly. But when you're running at a higher current, sorry about that, when you're running at a very high current and you're only running one, that means the power voltage and current has to come only from here and work its way all the way over. And that's why my 4 kilowatt amp that I built also uses two of them. And somebody, of course, is calling me while I'm doing a live. So just hold on again. Hello? Yeah. Okay. That's possible. Just a minute. Just need a phone number. Okay, just a minute. It's coming up. Okay, 417 394 394. Correct. 2022. It's 2022. The last. Yes. Yep. Bye. All right, I'm back. I thought that was going to happen, and I was correct. Alrighty. So now I'm back. What were we even talking about? I hate that crap when I get interrupted. I don't even remember what the heck it was I was even talking about. Okay. Well, oh well. Oh, the terminals. It'll just cause imbalancement in your power terminals. So always try and use both of them when you're actually running it. And apparently he only had one fuse going to the entire thing. And I don't even know if he had power going to both the terminals. And the wiring going back to the rear battery, the positive had 3 wires. So one coming in from the front of the vehicle to charge the battery, and then 2 to go to both positives, and then only 1 negative wire. And I couldn't figure out why, and I asked him, and it's because he had the amplifier connected to the chassis ground, but not to that battery, and he didn't have the battery connected to, he had the battery connected to chassis ground. Well, if you're running this big of an amplifier, and if you're running with an external battery in the back as well, if the battery's already there, do use the chassis ground with it, obviously, but also connect the amplifier directly to that battery. That way, the direct power from that battery, the full power can come into it, and then you'll have your chassis ground coming from the car chassis to charge your battery system. So that's just a quick thing to take note of. So now I'm going to show you a little bit about what I meant by center tap transformer. And now that I got the whiteboard out, just a minute, I gotta figure out what I'm gonna do here, because I minimize all this stuff. Okay, so let's go where to go. So an inductor, if you're looking at a schematic, will look like this. That is what an inductor will look like. And it looks similar to a resistor. And it's because it should, because a resistor is this. Now, resistors are used for DC uses. You can also use it for AC. They're used in crossovers, stuff like that. And voltage droppers for capacitive dropping or bleeding AC caps and such. But the inductor is used for active uses for reactive use, such as filtering out AC noise or SMPS noise from a switching mode power supply. Now, a transformer is simply one where you have a secondary in the presence of that same primary. And sorry about my penmanship, it's pretty bad today. Now, if you are actually building a transformer, this is called an air core transformer, and that's similar to a Tesla coil. Now, a iron core transformer is signified by having two lines, which signify an iron core. And again, I apologize for my horrendous, sad penmanship today, but means that it is more of a, like what's inside that big 300-volt power supply used for EMP research and stuff. This is a laminated core. So it's a bunch of iron plates stacked on top of each other very close, like just they're laminated first and then they're pressed together. And then that makes your core like an EI or an EL or whatever core it is. And it's just very thin pieces of sheets of metal. And they're laminated so they're not conductive. And that also helps to prevent magnetic inductance inside the core itself for eddy currents. And the lamination, the reason that's there is kind of to increase your galvanic isolation, but it's also so the eddy currents are not generated, or at least not generated as badly into the core, which accounts for energy power loss and extra heat, because that's when a power or a wire, when you put a current through it, so if your current is going through, so this is your positive input and this is your negative, well, technically, if this is the negative, then the current would be flowing this way. Because the people that taught you what electrons and protons do, I don't really know why they do that. I mean, I guess it makes kind of sense, and lighting is horrible. But what they say is that positive moves to negative. Well, actually, that is a pile of malarkey, because this stupid ass camera pisses me off. Because electrons is what moves due to them being a higher density of electrons than protons. So you have electron holes, and just like wind or water pressure, it pushes through. And I'm not going into that today. You can look up what all that is on different videos. But in layman's terms, when a voltage is put through a copper wire, the stray, what the hell is wrong with this piece of shit? When stray electrons are inside the wire, obviously, what the frick? This is really starting to piss me off today. Can't make this work with the damn, because that stupid ass light behind me. That's what I hate about that. Is that gonna work any better? Not really, but okay. The electrons in the wire are still in there, but the reason it's a conductor is because those electrons can be aligned, and they're free in there. They're moving around a lot more than in, well, let's say this wood, or this whiteboard. And that's because the electrons are not free. So when you push electricity through this conductor, what the frick? I swear I need to get a better phone or camera or whatever. What happens is when you put the electricity through that copper wire, it bumps into those electrons, and that interaction, just like in a filament of a light bulb, generates heat. While in here, it makes magnetism, and when that's called induction, laws of induction, and all that stuff. And that's why you hear inductors. Now, what happens is right now that's just an inductor. Even if it's just a very straight wire, it still generates that magnetic field, and it is flowing in this direction. So we're gonna go with the current that they teach in school. But you can't think of it. So the current will be flowing around the wire like that. If the positive is moving through. What the hell? That is a very horrible thing. There. Now, that magnetism is very weak because it's a stray wire. And what happens is if you have a secondary wire in the presence of that, boom, the electrons in this wire will then start to align with the magnetism. And that's also known as when the copper cuts the magnetic field. This is how generators work, alternators, even speakers. But you have a permanent magnet that interacts with the electromagnetic field. What the hell is wrong with this piece of shit phone? For frick's sake. Never had this much problems. You're listening to the interaction of the magnetic field itself, and this happens with a transformer. When the voltage comes through the primary winding, it makes a magnetic field and it induces it. Now, the reason it's a conductor is because it can also jump. The electrons that are induced can jump past the other electrons. Number one, they're moving around a lot more, and they're free. That means that there are more electrons in this conductor than there are in this. So that means that in the orbitals of the atoms, there are more electrons, so you have a higher electron cloud and you have a higher electron density. So since the bonds, the nuclei, they can't hold all that extra power, those electrons in, so they just bounce around in there. Now, obviously, since it's not necessarily radioactive, they don't escape, they just a party, if you want to think of it that way. But there. Now, when you have the secondary winding, those electrons are doing the exact same thing, but when the magnetism hits it, just like with a beam of plasma, it is magnetically and electrostatically manipulable because of the high electron clouds. And it's also ionized. Now, since the voltage is kind of like a higher pressure on one end, you'll hear electrovoltaic pressure, electron pressure, because that's back then what it was classified as. And it actually is that. It's just pressure. Electricity isn't necessarily power. It's not like a force like gravity. It's literally just when you have more electrons here than you have here. Now, obviously, physicists don't go crazy here. This is called an anti-electron, and this is called an antiproton. If you have an electron that is an electron, but with a positive charge, you have an anti-electron. But if you have a proton that has the same characteristics as a proton, but that has a negative charge, it's anti. So look that stuff up too. It's really, really interesting. Now, these transformers are slightly different than what I just talked about. And that's because they're what's called a toroidal core transformer. And this is what the transformer looks like on the bottom. All those wires you see. Now, obviously, you can't see any of it because it's on the underside of the PCB. So what happens is the primary is wound. Instead of having the primary on like one top of the bobbin and then another bobbin, it's actually wound on the same core, obviously. So it'll be magnetically coupled, but it's like a donut. It literally, the core is just a donut, but it's called iron powder. And that looks like this. If it is a schematic, you will see the core look like that. So it will look like this, and then that's not a resistor. It's just, I don't have good penmanship, so my wrist is screwed up. Now, the reason I say it's like a donut is because it's wired like this. That's your core. And the wire is wound around the actual coil, the core. Now, in the same presence of that primary winding, the secondary is wound all on the same one as well. Now, that's a very horrible representation, but you also have what's called the center tap, and that's where you see this primary. So let's call this positive and this negative. Well, or actually, in all actuality, if this was a single winding, that would be ground. Well, it's not. So we're going to cover that up. And then you have what's called a center tap. And that's why half bridges are used to drive it. And by that I mean the power, this is no longer positive and this is no longer negative. So we're going to negate that by just putting an X beside it. And this, the battery input voltage, actually comes into the center tap of that transformer winding. Now, what happens is you have a MOSFET up here, which is a switch, and then you have a MOSFET over here, which is also a switch. And I'll actually show you a real schematic. I'm going to draw one up for you. Hopefully you'll actually be able to read it. What the frick? This piece of shit phone. Now, since the voltage is coming into the center, and that's why I said last night, the voltage is sitting on both drains of the FETs. At the same time, it's just that mother humper. This piece of shit's gonna piss me off in a minute. I'll give it that. Fuck. Now you can't even see it. Here. Yeah, you can. Just a minute. If I do this. Okay, so it's a little bit far away, but I can fix that as well. So, you stupid ass freaking phone, you. So let's see here if I can even get this crazy ass thing to sit still. Maybe, I don't know. Okay, so now let's try and get this stupid ass thing to work. Alrighty. I think you're starting to slip again. So you will have the primary voltage come into the center tap, and then you'll have your two switches here, but they'll go to ground. And this one will go to ground as well. Now I'm going to draw a real schematic in just a minute. So since the power is sitting on both drains, that means that the voltage is, boom, across the entire primary, but not from the top. So when this one turns on, when it gets the high signal, or 1 if you want to go binary, then the voltage will flow. We're just going to go with standard current here, what most people would think of. So the positive will flow through this side, through this MOSFET to ground. Now, this one's not on, so it's just like this is not there at all, so it's not doing anything. Now, this one will now get a 0. And it is now low. And this is why you see what's called a square wave. Now, stupid ass phone. I get screwed up again. Now, this one will get a 1, or will go high. Now, that's where I said it's phase shifted. That way, only one is on at the same time. And then the dead time control, or DTC, of your driver ICs, you will notice that at one point in time, both MOSFETs will be off. Now, that is to be absolutely positive that both of them are not on at the same time ever, which will just be a direct short if that ever does happen. And this piece of shit phone is not. What the fuck? Damn it. This is really daggum annoying, I'll give you that. There. Now, the power will only go through one side, and then the power will only go through one side. And that's why it's called A, because only half of it is on, half of the transistor stage is on at one point in time. Now, let's say you want a dual rail output. Well, you do the exact same thing. You center tap the secondary. And no, just like on MIDI Segar's video, Electro Boom, that is not Uranus. So don't be thinking dirty here, okay? because someone came in his house thinking that was Uranus. And if you want to go and watch that hilarious ass video, the name of it's actually Free Energy Scam or something like that. Just go and watch his videos. They're really funny. He explains how electricity works and circuits and builds stuff, but he does it in a really freaking hilarious way. And this piece of shit phone, I'm gonna throw it out in the window, and then I'm gonna go to Springfield and get it because this fucker won't daggum work. I don't want it to be so dang far away. You can't even read it. Let's try to lighten it up a little bit. And let's try it again. Haha. Or it's lumpy. Oh. Now. Shit, I just drove over myself. Let's get rid of this so that we can actually build or draw a real schematic. So now I'm going to draw a half bridge. Now, the full bridge is basically a mirror image of that. It's just two of those. Same load, but you don't have to have a center tap. So a MOSFET is signified as this. And again, that stands for metal oxide field effect transistor. Now, FET is a term for field effect transistor. Now, if you MOSFET, you'll have metal oxide field effect transistor, but just like any other transistor, you have an in channel, or if it's a just a transistor like a BJT or a signal transistor, you'll have in. But then you'll have its counterpart, and a lot of the time they will, they will have their what's called complementary, and that means that the opposite polarity will complement that one, and that is called P channel. Or a with a PNP transistor, such as BJT, it's called PNP, which stands for positive, negative, positive, and that's what the doping is inside there. And again, you can look that up on your own. And I may actually do some videos about that later on. So you have 3 pins, which is GDS, which is gate. So we're going to call this gate 2. And again, quick rundown again. The gate is like the switch that turns it on and off. And we're going to call this one gate since it's up top. So I'm going to do that again because it's not supposed to be a 6. Gate 1. Okay. So since gate 1 is the gate, it turns it on and off. It opens and closes the transistor, allowing for the power, the electricity to flow through. So now we're going to make our center tap transformer winding. But first, we're going to draw the actual schematic, or draw the transistor itself. So what happens is you'll have a center point here, and then you will have this again. Now these are enhancement FETs, they're not depletion zone FETs, and depletion zone FETs, when you look at this gate junction, it is a broken line. And I kind of think of it as like the iron core transformer is solid, so this is an enhancement FET, and then the iron core, which is a broken up core, is instead a enhancement or depletion zone. Now, that is for a whole different episode. Just like FETs, there's JFETs, there's all kinds of MOSFETs. That's just like saying, I want a transistor. Well, there's a few thousand of them probably. Now, your transformer, oops, opposite way, this is not the secondary. So I will draw the transformer a little bit nicer this time. Oops, except for that. So now this is the inductor, and we're just going to use the common, wow, I can't draw a straight line to save my own life, or broken line. That looks like some drunk man was doing, painting a road. Sad. Now, the center tap is obviously what it sounds like, and it goes directly to power. And by that, it means that it goes directly to the positive, or the battery, and in fact it is connected straight to the battery terminal, the power of the terminal. So we're going to look at that next. So I'm just going to jump through here. and it's going to go through a fuse to power. That's pretty straightforward. So you'll have F1. Now, for these amplifiers, I believe each of the terminals is supposed to be fused at 125 amps. I can't remember. 300 in total. So here's your positive there. Then you have your fuse. Now, to drive the actual device, you have to have your transformer connected to the half bridge in a specific manner. So gate, drain 1, and source 1. So there you go. Gate, drain 2, and then drain 2. Okay. So I don't see anyone watching. Sadness. Anyways, you will. Why can I not think today for nothing? All right, since the power is coming through here, obviously, since it's positive, it has to go to the drain. Now, again, since a inductor, which is the primary of this transformer, it's basically a DC complete dead short. So it's 12 volts or whatever the power is at your car battery or car output coming directly to terminals is going to be sitting right there. Directly right there. Now, for ground, things get a little bit funner. Actually, it's pretty damn simple. You just simply go here, jump, and then you go down to ground. So I don't think you can see that. Nope, you can't. So I keep on forgetting. It'll go out of the shot. And that's not drain 2, that's source. 8 drain source. There. Now this will also connect to this ground plane. And yes, that is chassis ground. And by that I mean that's connected directly to the negative terminal of your amplifier, the input negative terminal, which is obviously connected to the chassis ground of your car, the negative terminal of your battery. So for years until I really started doing this, until I opened my business and did this work, I've been working with car audio for roughly 13 years. I always thought that these were some weird thing and I couldn't figure out how it worked. Well, it's pretty damn simple, isn't it? It doesn't have some current limiting. No, the current limiting is the inductor and the frequency coming to the transistor. Now, for this, the opposites coil just goes directly to the second drain. And that is why it is called a half bridge, because this one will be on and this one will be off. And then this one will shut off and this one will turn on. And then back and forth, on, off. So 1, 0, 1, 0. So obviously, since that's starting at 1, this one would be 0, 1, 0, 1. On, off, on, off, on, off. And it runs, I think this thing runs at 35 kilohertz. I haven't tested the power supply frequency just yet. Now, for that to happen, along with an inductor, what will happen is when this transistor turns on, a magnetic field is generated. So it will be generated and it will shoot into the core, which will cause saturation of the core. Think of a rag. You want to get it wet, right? So you don't want a little tiny stream of water. Otherwise, think of this. Otherwise, by the time you get it done, the other part of the rag could be dry. So I'm talking about like just drip, drip. By the time you get all the way wet to the other side of the corner of the rag, the first side's gonna be dry. So that's called saturation. So instead, you want to have a larger stream of water. That way you can wet the rag all at once. Now, that is when the core, or the rag, becomes saturated with the magnetic field. Now, by that I mean it's just like a capacitor. A capacitor does not have an infinite amount of capacitance. And By that, I mean like a 1000 microfarad capacitor can only store up to 1000 microfarads of storage. Sometimes it's a little bit higher, and that's due to tolerances in ESR, equivalent series resistance, and also ESL, equivalent series inductance. Yes, capacitors do have inductance. And that is also why the driver boards on these amplifiers, also for the output driver for the output stage, are S&D to decrease the amount of parasitic capacitances and the parasitic inductances between the actual components themselves. So like this component and component, well, that's a capacitor right there. And then the traces, and also even the let's say this is the PCB right here. So when you have your component and it solders onto the other side of the PCB, even if it is the same component, let's say, oh, a 100 nanofarad capacitor for timing your power supply, that makes its own capacitor, which causes issues. Well, the smaller the component, the smaller the components are inside, and that means that the leads are smaller and they don't through the PCB, which also comes very close to the chassis ground, which also makes a capacitive coupling. And if it's a very high frequency, and if your chassis isn't aluminum, that's also part of the reason your chassis are aluminum. Number one, for lightweight, so they don't rust, but also you would get massive inductances in your chassis. Because when this core, so when it becomes that cannot hold any more water, well, where's that excess magnetism going to go? Somewhere else. So that's also why the transformers are a donut, because then the wiring is wound around it and the magnetic field is focused and stored inside it, inside the center. So the magnetism doesn't just escape. It's also called shielding. Now that's why you'll even see toroidal core transformers used in home audio, because toroidal core transformers can output a larger VA rating for the same size of an EI core transformer. They don't have the same eddy currents, so they don't have as much power loss. They can be smaller, but have the same output power as a reference to its counterpart of an EI core or uh, a laminated core. Also, due to the low in eddy currents, you don't get as heat, so you get less power loss that way. But mainly, it shields the magnetism, and that's how magnetic shielding works. Instead of just having one, like a bar magnet, let's say you have a bar magnet, right? Well, this is your north, and this is your south. Well, that magnetic field is going to exit the north side. It's going to pull back around. It's going to be a lot farther than that. And it's going to go back around. Well, anything that is, like a transformer, that is in that magnetic field will detect it. Now, if it's an AC or anything that is being chopped, these are also known as DC choppers, because they chop the DC into a square wave. It is not an AC sine wave, so technically it is not alternating current. Alternating current is this. So this is your neutral plane. So we're going to call that neutral. Okay. So that is the voltage will fall to 0. And this is not your neutral portion of your outlet. This is just when this is the AC sine wave itself. So this is your positive, and this is the negative. I don't know how well you can actually see that. I don't know if you can see that at all. Okay, so you have your positive, and then you have your negative. And the reason it's called alternating current is because it alternates sinusoidally between the positive and negative rails correspondingly. Now, does that look kind of similar? Common, positive, negative, dual rail. Sort of. Kind of like the dual rail power supplies inside amplifiers, or many other transformers, or many other uses. And that's because in the generator, you have a rotor, And this is kind of like how an alternator works. This is exactly how an alternator works. And you have an electromagnetic field that is generated inside it along the core of that rotor, and it spins inside there. So let's say this is north and this is south. Okay. Well, that is a shitty alternator because that's only going to have one phase. But then you have the stator that is all the way around it. Now, an alternator is a transformer. It's called a rotary transformer because it takes in your 12 volts from your battery and steps it up to your 14.7 or 15 or 16 or whatever voltage you need. Now, this magnetic field, the rotor, spins. Well, it hits these magnetic fields. So the north is here, but then at a certain time, the north is here and the south is here. Well, as the north hits this side, it goes positive. And as it moves, it starts going down. So let's call this north and south accordingly, not 5. There. Now, what the heck? There. Crazy me. So you have positive and negative peaks. That's also why you hear 120 volts RMS and then 170 volts peak to peak. And that's because it spikes. Now, that's for later on as well. But as it rotates, it switches the polarity. Now, in all actuality, an alternator is built more like this. They have a very specific core. They do not have a center type primary. They have what's called an AVR, which is basically this, in a way, automatic voltage regulator. And you will have your core in your rotor, and it has multiple coil windings. Now, the way it's built is it's kind of like this. I don't know if you have ever taken an alternator apart, but you'll triangle core. Now, the cool part is as the core does that. So, here, just a second. I think I actually have one. I can just flat out show you. Okay, so this video is going to be long. This is just to show you cool stuff, you know, just because. Let's see here. I do, right here. All right. And it's already taken apart, so that no longevity there. It's quick and easy. I can pop it apart and show you exactly what I'm talking about. But an alternator is a transformer. It has a primary and a secondary. And it has a core, which is, well, it actually technically has 2 cores. And that's because it has the core for the rotor and the stator. And the rotor rotates, obviously. And that's also how you get a triple phase voltage jumper. Son of a bitch. Alrighty. So this is actually an alternator. Let's see if I can actually get this to work with the crap. Howdy, it's me. You got glasses on camera. Let's see if I can. Okay, so let's do it like this. It's easier this way. Here's the inside of an alternator. Yeah, I did that a little bit. There we go. Alrighty, let's see how well this will actually work. So as you can tell, the rotor, which is connected to your pulley here, spins. And there it is spinning. Now, this is called slip rings, and this is where the voltage is applied. That is a very low current and relatively low, like maybe a few hundred milliamps. Now, the reason I said it has that weird looking core, look, see? It has triangle shapes. Now, you can't really see it, but the wiring is actually wound inside there. So this would be the north pole, and this would be the south pole of the magnet. Now, this is an electromagnet, so it can be adjusted accordingly to the voltage output of your alternator. Now, it spins. So before this north one exits the point of active region, I'm going to show you that, this south one already is entering it, and so on and so forth. Now, this may look similar to a toroidal core transformer, but it's not. A toroidal transformer actually winds around. See the difference? Slightly different, but same principles. You see these little plates, these gaps. Well, this is an iron. I don't know how well you can see it, but you might see, aha, there. See those little gaps actually in between those pieces? That is what I mean. It's a laminated core transformer. Now, these are actually 3 windings, and that's why you have triple phase. Now, what happens is that magnetic field in that core passes over multiple of these at one time. In fact, all of them have a magnetic field passing over them at all times. And this line right here, this point, is called the point of active region. And that's where the magnetic field is focused into the core and into the wiring itself. Now, as it's pretty clearly visible now, you can see that it actually rotates, and there's the other portion of it. Now the other side of that little core right there is the same width of that. See how not one, and there's very little distance between them, so there's very little time that all of them do not have a magnetic field. In fact, none of them do. And it spins around, and that's how you get triple phase. But as it swaps from north to south, that's how you get the positive form and the negative form. Now, I know this may seem a little bit maybe in depth, I guess, but it's just so that you guys can understand how a transformer works, why it works, and why you even get a true AC sine wave. And that is because of that true rotation of the actual transformer. Now, or of the actual rotor. Now, also, that's how your generator works. An alternator is just simply a generator. That's all it is. It just runs off of a DC voltage to excite the coils, and then you have the secondary around it. Now, that is why you get a smooth AC sine wave, because it's spinning. So, a square wave does not dip into the negative region. That's why it is not truly alternating current. It's not just because it's not DC. It's because it actually alternates between its polarity. So I was watching Baravid's video a couple nights ago, and he said something about that, and someone kind of, I won't say they were being kind of a butt about it, but they clearly stated that, because he stated how he was talking about how these transformers inside the transformers in the amplifier run off of AC. They're driven by AC, and someone got like, oh my, no. He was just saying that it is not a DC voltage. It is chopped up, so it isn't DC. Now, you can drive these off of AC voltage, but very high frequency. These do not work for frequencies, which is 60 hertz in the US or 50 hertz overseas, and they run off of 240. Here, our wall outlet is 120, and then our industrial use, like dryers and stoves, 240. Now, my big power supplies that I'm building or built, they have to run off of 240. Now, let's talk about why they are actually driven by this in the first place. You'll see the difference between like a modified sine wave inverter, like this one, and a pure sine wave inverter. The reason inverters are so, I don't really know how to say this. The reason inverters are so, there's so much controversy about which one to use and all of that stuff is simply due to the output waveform. Now, this makes a square wave on each side. It does not change polarity, it just changes when it is on. So you can tell by the sequencing here. Now, a modified sine wave looks like this. An actual modified sine wave that's not just a varying voltage, that's not just a pulsed square wave that is phase shifted. And that's also when I build amplifiers for people and they say, well, I want it to be bridgeable, so you have to shift the phase. And a lot of people think that just means that you just swap the polarity of the inputs on the RC. Oh, no, no, no. No, 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 no. That means you actually have to change the phase where you move the sine wave over so that this side is on and then this side's off and then this side turns on, and that's how a bridging amplifier works. But actually, a bridging amp is a full bridge, and I'll show that in just a few minutes actually. Now, an inverter does this slightly differently. Same technology. In fact, this amplifier is technically an inverter. Amplifiers are inverters. They output true, pure, clean sine wave. They really do. That's why they sound good. That's why you can run speakers off of them. But it's analog output. That's why Class D has just blown up all over because it's a digital use. It's a square wave that is fed. If you remember the video last night, I'm not really going to go back into that today until we get to the driver necessarily. And it's modulated accordingly to your AC sine wave. And by that, I mean, let's say I'm pushing a 1 hertz, let's say a 20 hertz wave. So let's look at that. And it looks like this. So your square wave would look like this. It's positive, or it's on when the sine wave is low. Ah, shit. Screw that up. I can't draw a sine wave with shit. I'm serious. So, okay, you get the point. When the sine wave is positive or high, it turns it on. Now, when the sine wave goes low, that's when that side would turn on, except you don't have a transformer on the output. Now, that is what I mean by phase shift. You don't swap the polarity. No. You just simply switch or you just simply swap the position of when it's on. So when this goes negative, the second stage goes high. Now, the reason you get a AC output on your output stage is because it's running off of a dual rail power supply. And when these sets of transistors turn on, it pulls the power high. So it opens positive, corresponding to neutral. Now, when it goes negative, it turns this transistor on. This is a half bridge, and they are used in a lot of Class D amplifiers still because they're so easy to use. But this amplifier is actually a full bridge, which is exactly how an inverter is built. It's just it doesn't have a locked has its own oscillator. Like I said before, it's a local oscillator. It generates a high power. Using this, actually, it uses a transformer, and it charges a capacitor just like in an amplifier. The power supply isn't really the special part at all. It's just a PWM that steps the voltage up using transformers, rectifies it, and puts it into capacitors. What's done after that is the difference. That's what signifies an inverter from an amplifier, from a Class D to a Class AB to a Class A, whatever it is. It's just the power supply is just to take the low 12 volts high current and step it up to a high voltage. Just like a transformer plugged into the wall can to plus and minus 60 volts. So you get 120 volts, but it's a dual rail, boom, boom, of 60 volts, plus and minus 60 volts. It's just a transformer, that's all. So for an inverter, it has its own quadrature oscillator, and those ICs generate a square wave that drive these transistors, which drive this transformer, which is, oh yeah, also center tapped. Power goes in here and then switch and switch. And then these other ICs, they do talk to that one as well, and it turns these transistors on and off. And the reason there's 4 is not because these two are in parallel and these two are in parallel. No, no. Each, they're all on their own. And I'll tell you about that in just a minute. They're not like this. One half of it is like this, actually. So, but the low goes directly across here. So just a minute. So when the positive, when you have the inverter on, it generates its own 60 hertz signal. And it feeds the gates of the transistors all on its own. You do not give it an input signal, so it's not amplifying an external source. Local oscillator. There you go. Now, modified sine wave looks like this, and I'll just show you real quick because it's easier that way. Looks like this. Square waves. So you have a square wave, and then it moves over, and then you have another square wave. You have a square wave, moves over, and you have another square wave. Boom, boom, boom. Now, positive, negative. But it is going to a neutral zone. So it is an alternating square wave. It is going positive and negative. That is why inverters are very controversial in why people are so controversial in what you want to use. That's called a modified sine wave or a simulated sine wave. It's simply two square wave signals like these put together, but this one's phase shifted, so its low is the output. But, okay, that was a little bit confusing. These do not run off of a dual rail power supply, some of them. A lot of the cheaper ones run off of just a single rail high voltage power supply, like 150 volts. Now, with a certain design, you can turn this into what's called a pure sine wave. And in all reality, it actually technically is still a pure sine wave. A pure sine wave is where it is a nice, pure, stepless sine wave. I call it a stepped sine wave. And that's because, so let's make our neutral zone again. Okay. All right. So you have positive and you have negative. Okay. Now, as you start going up, you go up a little, then you go up a little more, and then up a little more, and then up a little more, and then up. And then it goes back down with the same oscillation, with the exact same timing. You go down, and then 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 down. Now, as you could tell, that is not smooth still. It is actually still. It's using, it technically is still, it actually is a sine wave, but it's stepped. So you have high, and then it moves over, higher, moves over, higher, 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 and then it goes backwards. Now for the down state, it's exactly the same. So it just goes steadily down. And the reason I call it a stepped sine wave is because it looks so much like steps. And that's because that's exactly what it is. It's stepping downward until it goes, damn it, until it goes down into the negative range all the way. And then it moves over, and then it goes right back up. So you have your positive peak here, you have your neutral here, and then you have your negative. Now, that is a lot better to use, and I'll show you why. So let's peek back at our modified sine wave. Notice how that's really sharp, and that's what you don't want. Rectifiers will be okay with that, but you will notice a bing. You'll notice a, it's not a hum, actually, it's a buzz. Microwaves will work transform, but as well, because it's not a true clean sine wave. It's just a chopped DC, but you're getting a negative signal as well. So it is it is an alternating current, just not pure. Now this is why you will see people go, well, you don't want one of these, and I'll show you exactly why. So you go from the neutral. Now we'll go from, yeah. Oops. Sorry about that. So you go from neutral down to positive, down to neutral, I didn't work with a hooey. Sorry guys, I can't hardly draw today for nothing, so I made it too small. So let me try that again real quick. So first I'll just draw a sine wave. It's still crappy. Oh, sorry guys. Nope, it has to be wider so I can actually show you what I'm going to show you easily. Bear with me here. Now, you guys probably, if you're watching this video, you probably actually have already seen a lot of what I'm talking about here, but some of you may not have already seen it. Now, let's make our modified sine wave. So it goes over, steps up, then over, then down, steps down. Now here's the neutral, and the neutral is a dotted zone. That way you don't mistake it for the low side of the square wave for either side. So then it will move over, come down. Either you'll have that problem where it exits where the sine wave should already be going back up or back down. So normally that's not the problem. Instead, this is the issue. It moves over, and it does actually go all the way down. Now, this is also why, if you don't have what's called a true RMS meter, this will not be detectable properly. And I'm not going all the way up so you can still see the dotted line that's signifying neutral. And then it goes up, over, and then down. Now, do you notice how there's power that's not being used? There's a lot of power being, number one, lost, and just flat out not being generated. That right there is why it's not good. And the sharp corners make it very, very bad for sensitive components, especially like radios and certain amplifiers, especially digital amplifiers. You'll have lots of issues with the amplifier. So even with just regular amplifiers, you'll notice it because the rectifiers are obviously not perfect. And this is 60 hertz, but it does have a sort of, I guess you could say, somewhat a higher frequency superimposed upon it. Now, this, as you can tell, when I just make a standard standard sine wave. Notice how close that looks? I mean, it looks so close. Well, that's because it is. It's a lot better. It's a lot closer. The signal is much smoother. But because it doesn't just use one step for the high, one step down for the low. And that's why those are so poor. But that's also why Class AB amplifiers are so inefficient, because Class AB amplifiers do this. They don't turn your AC analog signal that gradually varies down and up and down in signal and amplitude, and then it's varying in frequency as well if it's an actual amplifier. Instead, these turn into a high frequency square wave at a certain frequency, and then they adjust the pulse width. But the transistors are fully on and fully off to their least amount of resistance and their highest amount of resistance to where they're off. So it's like they're opened. Now, in a BJT amplifier or even amplifiers that use MOSFETs on the output stage, it's analog. So the transistors are kind of acting as variable resistors. They have to, they're not modulating. Well, they're modulating, yeah. They're actually having to open and close and change the resistance accordingly to the impedance, according to the AC signal slope and its frequency and its amplitude. So you have the transistor running at 100 ohms or whatever resistance. So it's like the difference between a buck converter and a linear voltage regulator. Yeah, linear regulators, you don't get the noise that is generated by a buck converter, but you waste so much power. So a buck converter is better for battery powered uses, while is better for if you have a very large heat sink or like in an amplifier where it's plugged into the wall or a car amp. Now, these pure or step sine wave, I cannot believe I actually do that well. It's not very well, but it's a lot better than I thought it would be. Since they have so many more divisions in them, and they actually have a lot more than that. So when you draw a real sine wave over it, you have a lot less power that is being lost. As you can see, there's very less. See, here is a point of this non-active region right here. Very bad. Now, it's cheaper, yeah, because the build is easier to do, but it is more efficient because the transistors are fully on, fully off. Here, it's more of an analog signal. I call it a hybrid. It is still going up, over, but many, many more times. So the MOSFETs are actually changing the resistance, or, well, I wouldn't say impedance because they're not being fed by an AC signal. They are actually feeding off of a DC bus, not like this, actually, kind of like that. But they are way more expensive. They're because they have to have bigger components, they have to have better components, more of them. The drivers are more complex. And they have to have better feedback looping to monitor the voltage. Their dampening factor is not as good. So if you have a certain load on a modified sine wave, you will have a lot of ringing. If it's like a transformer, you'll hear it really badly, and the voltage can even spike out of the active linearity region of the sine wave that's supposed to be being generated. So it's supposed to output 120 volts RMS, right? Well, sometimes it can jump as high as 150 to 160. Well, that's not really good. These are a lot better because it's not just straight up. So it makes your transformer go wham, and it just boom. So the transformer just gets punched. So it makes a very large impulse into the secondary, and that's why you hear that instead of like a hum. And the same thing happens in the secondary. You get very sharp pulses in your secondary output stage of your transformer, so your rectifiers cannot work as easily. Now, it might be a little simpler on them because it's a DC coming through them, but they're designed for AC voltages, so you have to have high-speed rectifiers. And also, with a true sine wave, since it's a pure sine wave, it's gradually increasing. It's analog. The transformer's fluctuating instead of just pulsing. Kind of like the difference between a pulsar transformer and a standard transformer. Very big difference. Now, let's take a look at an amplifier design. An amplifier design is almost identical to this. It does not output a square wave because that's DC. Your speaker will just pop and it will sound very badly, and you'll fry your speakers and you will fry your amplifier because it's straight down, straight up. Whoa, that right there is DC. There's no modulation. Now, Class D does turn it into a square wave, but it filters it back out. So we're going to look at it because it's closest to an inverter. So keep in mind of this. So why can't you just use an amplifier as an inverter? Well, I've asked that question a few times and I answered to myself. An inverter has what's called it's kind of like PLL. As you put a load onto it, it constantly switches to make sure the voltage stays high enough. But it is designed for transformers. Transformers do not operate the same way as a speaker, whether it's even a tweeter, unless it's unless it's one of the little stupid piezoelectric tweeters. I'm talking about dynamic drivers only. But we're looking at sub. Subwoofers have big voice coils, low inductance, but high power, low resistances, but they have a magnetic field that they're interacting with originally. So they're pushing up against that, which is also generating a back voltage. So as the voltage is going into the positive region, the cone is going to move up. What the hell is that? The cone, or the coil armature, is going to move up. So positive and neutral again. But as it goes down, as it goes negative, the polarity of the magnetic field is going to swap. While the polarity of the permanent magnet obviously does not change. It stays the exact same. So with the magnetic field changing, it pulls that coil down. Well, if it's a square wave, it's going to go straight up, straight down, all the time. With an AC sine wave, it's going to impede that because it's a voice coil made of copper, and it's reacting to that magnetic field. But here's the difference. An inverter does not have a what's called voltage. It does because the voltage does go back to neutral, but as just like in this transformer right here, as it is energized, it makes a magnetic field, but as the gate is taken to 0, there is a dead time. So at one point in time, both of those are at 0. Both MOSFETs are off. But before this one goes back high again, so here's your high, here's your low, and this one's going to be low as well. But then this one goes high. Well, before all that happens, that magnetic field has collapsed and has fallen back down onto the coil, onto the inductor. But here's the thing. This primary is also in the same presence of that magnetic field. It's wound, it's interwoven, as you can tell. It is interwoven. So the secondary, regardless of which side is on, both secondaries are going to output a voltage. That's why the rectifiers are designed how they are. It's called common anode and common cathode rectification stages. Now, that means this is going to generate a magnetic field opposite of it's going to generate a voltage opposing the voltage that was inserted upon it. That's Lenz's law. The magnetic field generated will oppose the current input, the voltage input. Now, what does that mean? Well, the 12 volts is still sitting right there. And the ground is still sitting right here. And the positive is still sitting right there. Well, if that has flipped, it's backwards polarity here, but the power is still connected, but those are both off. So it's like they're not even there. Well, then it makes a very high voltage here. And because when it collapses, it's like running that voltage system in series of itself. So you will achieve a very high voltage, and that's called inductive spiking. And that's why in an amplifier, you'll see a diode. So we're going to take this here. Wow. Well, that sucked, like indefinitely, and not in a good way. So let's try that again. So let's go to ground. Now, you'll have what's called a flyback diode, and or a snubber diode. So you'll have the diode come here, but the anode, a diode works by allowing voltage to move in only one direction. And no, not like the band either. So with a diode, if you've ever seen one, you'll know what I'm talking about. The line signifies the cathode, or C, and the all black side signifies the anode, or the positive. So a diode is used to allow current or voltage to flow in only one direction. So you take that diode and you place it directly across the terminals of the battery, or preferably right across there. Now, you may be thinking, well, why would you want to put that diode there? It's just going to directly short. Well, I didn't tell you the whole story. Well, you don't want to connect the anode to the positive, obviously, and the negative, or the cathode to the negative. It's just going to short the hell out, right? Well, that's why you do what's called a reverse bias. You take the cathode I don't know how visible that really actually is. You take the cathode and you put it to positive, and you put the anode to the ground. Well, what that does is, number one, it's like that diode's not even there. It's reverse biased. It's not going to short out unless the diode is not designed for that high current, because that's a very high current with low voltage. Well, if the current is too high okay, take it. It's a check valve. So you have a check valve, right? Let's say it's designed for 10 psi. So it allows the air to flow in one direction, but then you can put it into a tank, and the pressure from the tank can't go back into the air pump, right? Well, that's how those work. Well, let's say it has increased, like someone hooked up a different pump and didn't know it, and the other person didn't know it, but it can take it up to 30 or 40 psi. Well, this thing is going to try and make sure that air pressure cannot go back, just like this. It's going to make sure, so you can, that's how rectifiers work. So you have an AC signal, or you can have your positive voltage input, VI, coming into it, and then you can have like a capacitor, whatever, here, and then this will be going to ground. Well, that is, well, that's a peak detector, but it's also a very easy reverse voltage protection. So if you forward bias it, you apply your battery power positive through here. It goes through the diode, minus the voltage drop. Otherwise, actually, for some reason they did it that way. It stands for forward voltage drop. As the voltage goes across the diode, the depletion zone, there will be the voltage drop. If it's silicon, it'll be approximately 700 millivolt drop, which is pretty significant. That's why I use Zener and stuff like that, or I mean Schottky, but they all have their advantages, but they have their disadvantages. Reverse it, what will happen? Well, this will be getting negative. Well, it can't go anywhere. Well, that's the same thing that's happening here. So what happens is your diode also serves as a reverse voltage protection here as well, but a very poor one. If you're a smart car audio person, you will have a fuse, right? So you have a fuse right here in series with your power to your transformer to everything. As long as everything is connected properly, the voltage will just ride past that diode like nothing is there, as long as the leakage current isn't very high on it, which it shouldn't be at all. Not for this. Now, if you reverse the voltage, oh no, I've drank a few too many Smirnoffs and this turns to negative all of a sudden, and this turns to positive. Well, look at what just happened. You just forward bias that diode. Bam! It shorts. You will notice a very large continuous spark on your terminals. If your amplifier has very large capacitor bank, you'll already see that spark, but it will go away. Well, if you have a fuse, when that diode, it will allow a very large amount of current to flow through it. Now, either it will completely dead short, like blow up and dead short, which will mean that it will short the inputs and also blow your fuse. Now, in the worst case, it will open. And by that I mean, it will be like that piece of silicon is not there at all. So if you hook that voltage backwards and you leave it there long enough, it will shoot right into everything and blow your MOSFETs up, because then negative voltage will be going here and go into the drain. That's not supposed to happen. It will shoot right through the diode, through the transistors, and bam, it'll blow up all your driver ICs. Don't do that. So you want an adequate fuse, but not so large that if you do something wrong, it will actually cause it to fail. This is only good for instantaneous reverse voltage protection, because the voltage just rides right over it. It's not in series. You don't want it in series, because number one, you'll have that voltage drop, but also you have to have a big ass freaking diode to supply enough current to the multiple transformers, because this is only for one side, for one transformer. And this amp we're talking about has 4, and there are times 2 MOSFETs per side of the transformer. So we're going to call this L1, coil 1, and this one L2, coil 2. Same primary, but 2 windings. So that is why that diode is there, but that is not only there. That is for if you have, and it's out of focus again, sorry about that. You will back EMI. So like I said, that voltage is going to fall back onto the primary and it's going to generate that high voltage. Well, if you don't have anywhere for that to go, like a snubber network, whether it's like a snubber capacitor resistor network, or if it actually is a diode, I recommend a network of all three. And this amplifier, I actually don't see any snubber diodes at all. I don't see that diode in this amplifier at all, which I do not like. Normally, they're literally soldered directly where the terminals are at. That way, the highest current, if the voltage is either reversed, will go through that diode. And also, sometimes when I build custom amplifiers for people, I will put a diode right at the terminals, at each terminal, not just one for the entire thing if it has two sets of terminals, one or two at each side. Very high current diodes, though. Very high current. That way, if you voltage, the diode can deal with that current for a short amount of time. It's going to be short still because my batteries can deliver up to 1,000 amps continuously. So you want that thing to be able to deal with enough current for you to go, oh shit, I just did that wrong. Because that way it will be sinking most of the voltage and current through itself instead of through everything because it's just in parallel with terminals. But I also put a diode at every single transformer. Now, since this is positive input, you want crazy me. You want a diode to be there. And that was a very poor diode. There we go. Wow. That's now what that will do, the supposed to go through here, right? And through there, through the inductor, or through L1 and through the transistor to ground. Well, the diode is reverse biased across this. This is called a flyback diode. You'll see this in flyback transformers, and that's not where the name came from either. Like if you're driving, like if you're building a Tesla coil, if you're building a transformer driver or whatever, you will see that. Or, okay, a relay even, or a motor. When you turn that relay on, tink, it's got a core, it's got an inductor, and it's energized. And when you let go of the switch, whether it's a MOSFET, probably, you let go, tink, all that magnetism, wham, it's going to fall right onto that core, and it's going to fall right onto that primary, and it's going to generate even hundreds of volts. It's like this transistor's not even there, and we're just going to skip that for this little explanation. And you have your power come in to, okay, let's just here, yeah, the power would come in, it would go through the inductor, through the transistor to ground. Well, when this opens, so let's say this has opened, then it's like that's not there. So a very high voltage potential is produced here. That's how boost converters actually work. Now, what happens is it will overdo, or it will the voltage will overcome the depletion zone of your transistor, regardless of what it is. It will be voltage of basically what it can block before it just the hell up. And that's how people burn up their MOSFETs or Indian little transistors, whatever. But this diode, when that's shut off, when that falls, since it is not forward biased, otherwise it would just the voltage to go through the diode and bam, right through the transistor, knowing you blow your transistor up. They don't have enough inductance. Very, very low. Not like these. These are very low, but still, those are pretty much zero. They do have some parasitic inductance, but not like these, obviously. They're not copper, they're silicon. It's just like the leads and the. Anyways, so you reverse it. So the positive has to come, but it's blocked by the diode, so it still goes through, but when it shuts off, that reverse voltage has somewhere to go because as it is energized, it will make the magnetic in one polarity. But when it falls, it's cutting the copper windings oppositely. So when this would normally be positive, it's all of a sudden negative. It's backwards. Look at that. Anode, cathode, and it shorts across the diode. And that is why those flatback diodes are there. And that is why amplifiers are designed to run with subs. Because you have a big ass permanent magnet. Very strong magnet. Well, that coil, like I said here, is going to be moving up. When it goes back down to neutral, there's no voltage input, so the coil sets back down. But it's not being pulled down by the negative just yet. It's just going back down to its ground or resting state by the suspension. Well, as the suspension pulls it back down, it is cutting that magnetic field, making an opposing. It's making an opposite charge. It's making an opposite sine wave. So your amplifier has to be able to deal with that. And it does that with compensation networks. It does that with snubber networks across the terminals. Now, inverters, they don't have that actually. They don't have well, they do, but they do it differently. Now, amplifiers cannot be used as an inverter directly because of their I don't really know how to explain it necessarily. They're designed to power a that has its own push and pull and it has its own peaks and troughs, while a transformer is a very steady low impedance short. Now, yes, you can actually do that. You can, if you have a big enough amplifier and you have an amp that's, let's say, quarter ohm